Good morning. First, can you hear me okay? Yeah, okay.
Yes, sir.
Let me see if I can share my presentation here. Can you see my presentation?
Yes, sir.
It doesn't seem to be moving forward. Let me just stop sharing and just go back to that. Hold on just a second while we get the technology sorted out. Otherwise, I'll just present without the slides. We'll see how we go here. All right, let's just see if we can do this. Okay, so if we go to there and share. Okay, now this doesn't seem to be moving. Does anyone know how I get it to move forward?
So you can use your arrow keys on the keyboard.
Yeah, okay, let's see if that works. No, it doesn't work. That doesn't work. Hold on, let me just.
The
No,
down.
that's not working. For some reason, my slides won't work.
So you can either share the entire screen, or you can share through the special window. So you can choose either of the two options. But if you choose the entire screen option, then in that case, you'll not be able to see the audience. You'll only be able to be in the presentation mode.
Let's see what happens if we do that. The entire screen and share, that might work. Let's have a look. No, that doesn't work either.
You can just switch on to the presentation. So that way you'll have to go to the presentation mode.
Okay, bear with me, everybody. My apologies for this. Okay, if I go to the window, all right, and I pick the display, okay, and share, right, share.
So the left, right arrows or the up and down arrows should be able to help you maneuver.
Yeah, it doesn't seem to want to play. Okay, let's not, what does that one do?
Ask him to turn on slide. Sir, please turn on the slideshow option. Please, at the top, there's this slideshow bar. Please navigate there, and there would be an option.
Okay. Let me maybe do it a different way. Let me just perhaps, yeah. What I will do is maybe talk without the slides, because I think we'll spend so much time trying to organize the slides, that'll take up all the time, okay? And maybe talk about new energy materials in a general sense without using the slides. So first of all, it's
sorry for interrupting you, sir. If you want, you can share the slides with us. We will navigate the slides for you, and you can keep on presenting.
No, don't worry about it. I can talk. As long as you can hear me. Yes, I can talk without the slides. That's not a problem.
Sure, sir.
It might even be better. It might even be better. You never know. Okay, let's see.
Sure,
okay,
sir, sure.
So we're talking about new energy materials. First of all, what is an energy material? An energy material is something that can give you advantages in terms of efficiency, lower cost, lower weight, less toxic materials, more sustainable materials, etc. So it's a huge gamut of different things. And fundamentally, what an energy material is something that aids the conversion of one form of energy into another, or aids the transmission of energy from one place to another, or enables you to store energy. And indeed, fundamentally what it's about is, if you look at renewables, for example, which are highly distributed, you've really two choices in getting what are called high capacity factors, high matching of the supply to the demand. You can either move the energy in space, in other words, transmission. So, for example, the sun is always shining somewhere. So theoretically, you could move the energy from where it's produced to where it can be consumed. or you can move it in time by storage. So effectively, you're storing the energy from when it's produced to when it's used. And technologies for transmission and materials for transmission, so thinking about direct voltage transmission, superconductors, etc., essentially to compete with new technologies for energy storage in terms of those two aspects of trying to get a high capacity factor, a high amount of matching of renewable energy supply to a load. So there's a whole gamut of possible technologies that can exist in that area. New technologies are also a complex set of things in that the attributes that you might have which might be desirable in one respect are contradictory to the attributes you might have in another. So you might, for example, want a material that has higher energy storage density, is more efficient in both charging and discharging, for example, in a storage application, but it's more difficult to obtain, has geopolitical implications in terms of where it's sourced from, may be toxic. And so often with new materials, there's a trade-off between the attributes you want to achieve from a technical perspective and the wider environmental and economic factors that come into play, health factors as well, for example. So in choosing energy materials, there's a huge variety of different factors that come into play. Also, those factors change with time. So if I give you one concrete example of that, over many years, there were new materials being developed for concentrating solar energy onto photovoltaics. And the reason for that is that photovoltaics were expensive and concentrators were very cheap. And you get very cheap concentrated materials made out of polycarbonates, polyacrylics, etc., as well as glasses, etc. What has happened, as we all know, is that the cost of photovoltaics has gone down very, very rapidly. And that means that photovoltaics are now cheaper than concentrators. So developing new materials for concentrators, except in very particular applications where the particular type of photovoltaic works better under a more concentrated flux, is no longer a good idea. So the changing cost of different materials has changed what opportunities there are for materials in those applications. And you can see similar things in many, many other systems. But I can give you some examples of where materials are continuing to develop. One of the key challenges in photovoltaics is their thermal behavior. And as most people in this room will know, that the efficiency will be going down for typical solar photovoltaics by about 0.5% for every degree Celsius temperature rise. Now that is inherent to photovoltaics because there is for a single junction, for a single external junction, you're going to have what's called a Schottky-Kiesel limit, ultimately a limit of around about 32%, and the rest of the energy is going to produce heat. That's just a thermodynamic reality. So a lot of the issues to do with photovoltaics are to do with their thermal management. And so you see a lot of new materials being developed to do the thermal management of photovoltaics, and indeed a lot of new applications. So for example, if you look at new applications, for example, agri-photovoltaics, where photovoltaics are matched to agricultural production, or floating photovoltaics, the advantage of those, as well as making better use of land or water, is that in both cases, transpiration, when you've got agricultural photovoltaics, or evaporation from the water beneath in floating photovoltaics, are cooling the photovoltaics. So you can do system perspectives of how to cool them. But there's also a lot of technological interventions, one of which I was responsible for originally conceiving and developing, was the use of phase change materials to cool photovoltaics. And essentially what happens there is that you have phase change materials which change from solid to liquid at a melting temperature and absorb a large amount of latent heat at that temperature. They radiate through the photovoltaics to the night sky, are solid at the beginning of the day, and then provide a heat sink for the photovoltaics over the course of the day. And that sounds very simple to do, and indeed, in essence, it is. But the realities are much more complicated. one has to make very careful choice of the phase change temperature, such that you're not absorbing heat from ambient, you're absorbing it from the PV. And you've also got to get very effective heat transfer into the phase change material. That's more complicated because as the phase change material melts, the melted material floats and convects within other material in the phase change material, and the phase change material effectively acts as an insulant. So a lot of activity around new materials in that application is around enhancing heat transfer, which you could do with various augmented heat transfer services, like fins, for example, but also introducing things like nanoparticles, larger conducting elements, etc. Or indeed looking at multiple phase change materials, encapsulated phase change materials, etc. Also, these systems are going to go through lots of cycles. Every day they're going to be melting, and then at night reconstituting with radiation of the night sky, the next day melting, etc. So one of the big challenges with these kind of materials is that they don't supercool. In other words, they actually do re-solidify, that they could maintain their both the heat transfer characteristics and their latent heat characteristics over multiple cycles. So lots of activities around those kind of materials. Now, one very, very strong example of an application of new materials that is critical to the long-term performance of photovoltaics, but ironically is not a photovoltaic material. Similarly, batteries also have thermal management issues, and similar kinds of systems can be introduced there. The key challenge there, unlike the challenge in photovoltaics, is that many battery systems are to do with mobility systems. They're to do with electric vehicles and such like. And so weight becomes an issue. So in addition to the factors of getting good heat transfer, good latent heat to remove heat, etc., one's also looking to get a very, very low weight of the system. Now, that also can be accomplished by having a very high latent heat because your storage volume reduces. That then presents an issue because the highest latent heats are at the elevated melting temperatures, and most of the phase change temperatures that you need in most applications are not at high temperatures. So again, gives you some illustration of some of the complexities that emerge. Another particular opportunity around new energy materials is nanomaterials, quantum devices. There's a huge number of reasons for this. Quantum phenomena themselves can present certain opportunities for absorbing radiation at one wavelength, re-emitting it at another wavelength, which gives you new opportunities in terms of photovoltaics, in terms of collection systems, in terms of being able to manage rate of heat transfer. Also, you've got in certain nanosystems very large available surface areas at the nanoscale, which gives you opportunities for supercapacitors, for electrical energy storage, and indeed for holding certain molecules in place and releasing them with certain stimulus in the system. So quantum effects, nanoscale effects are introducing a whole range of new materials, both in energy storage and particularly in photovoltaic energy collection, and indeed in devices for light management for photovoltaics. So a lot of things emerging in there. If I can give you one example, you're now seeing what are called luminescent solar concentrators, where you have a material, a dye or a quantum dot. Quantum dots will be preferable to dyes because dyes can degrade in ultraviolet light. And what a quantum dot is a small molecule. You could vary its size, you could engineer its size, so that it absorbs and re-emits at particular wavelengths. And any particular solar cell, for example, has a very particular response to the spectrum. Up to the band gap, it'll absorb very efficiently, and that absorption will decline away from the band gap. With a luminescent device, one can absorb radiation at a variety of wavelengths, and with the quantum dot, for example, by engineering the size of the dot, re-emit at wavelengths that the solar cell can accept. So the parts of the spectrum that are normally not absorbed by the cell become absorbed by the cell. And actually, interestingly enough, for solar cells, for example, organic solar cells which degrade in UV light, you use the same phenomena to move the UV light to be in part of the spectrum where the cell can use it rather than be degraded by it. Now, one interesting thing about these kind of systems is that you can engineer them such that if you had a window, for example, in a building, you could let the visible light through, the light that sits in the visible spectrum. The rest of the light can be re-emitted by luminescent material on the window outside the visual range, so you don't see anything happening. But that light is going to the edges of the window, and solar cells can be placed in the edges of the window, in the surround, in the frame, okay? And effectively, you've then got a transparent window in the visual range, and indeed you can control that transparency such that it just lets in the light and doesn't let in the heat, okay? Or the rest of the instant radiation is transmitted transversely through the glazing, through re-emission from quantum dots, and is collected at the edge, okay? Now, this in itself then presents an opportunity in that you've now got a window that is both letting light through and collecting solar energy, a transparent window and it's collecting solar energy. And one particular application of that is then actually having a switch of material. And there are a variety of switch of materials, from suspended particle devices where particles are reoriented in a magnetic field, so that one orientation will let light through, and another orientation the window is darker. It's not entirely dark, but it has a level of opacity, and you can control the solar gain. Now that requires electrical power, and if you have a transparent window which can generate its own electrical power, it can produce the power to control its own transparency. So you're seeing here a occurrence of new materials that are both allowing you to redirect light to solar cells, alter the spectrum, and slightly more efficiently, and then electricity those cells to then power a switch of material which then can alter the transparency of the glazing to avoid overheating, to avoid glare, or to provide privacy. Okay, so a whole range of new materials, and you're beginning to see products in glazing systems for energy efficient buildings, in the climate I'm in, to let in solar gain and allow heating, in other climates, for example, to just let in light, reject heat, and indeed reject heat to the night sky at night and produce cooling sinks for the next day, etc. A whole range of possible applications there. And that idea of also rejecting heat during the day is also gaining a lot of traction, with a whole range of new materials seeking to exploit the long-range window to the sky that always exists. There's always about 40 watts per meter squared coming from a surface, even on a sunny day, to the sky. There's always a radiant heat transfer there. But normally during the day, it's overwhelmed by the solar gain in the rest of the spectrum. But if one device spectrally selective devices, one can get systems that even in sunny conditions are cooling to the sky. Now that's common at night, as many of you know. A clear sky at night will produce range of cooling which will produce ice on the ground the following morning, even though the air temperature is much higher. This is doing that during the day, okay? And again, new materials of that kind of application. So there's a whole range of new coatings using quantum effects that are seeking to manipulate the spectrum in photovoltaic applications, in switchable applications around glazing, and in applications to seek to have radiant heat transfer to the sky for cooling during the day. So a lot of factors in those. Now, if I just step back from those examples and look more generally at what the challenges are. As I said earlier on, a lot of the challenges with new materials is not simply their technical characteristics, and there tends to be a lot of research on their technical characteristics. So, are they more efficient in doing what they do? Are they reliable in doing what they do, etc.? Those kind of things are very heavily researched. What is less researched, but is equally important, is the kind of trade-offs. If you look at things that are going to be put into buildings, for example, and indeed in many applications, the flammability and the toxicity of materials becomes very, very important. And many of the materials that are developed do not have those characteristics. So they might be very interesting in the laboratory setting, but are not going to go to the commercial setting because the toxicity and flammability issues mean they're not safe to apply. So that's one dimension. But the other dimension is the dimension of the design and packaging of systems to use those materials. And this is an area which needs a lot more research because there are ways of using materials that minimize the amount of material you use, and there are equally ways of using materials which do not do that. If I use an analogy, one can have structural systems that are composed of solid steel elements, okay? But you can get equally strong structural systems that use tubular steel elements. In a tubular steel element, there's a lot less metal, okay? Well, the same applies when you're looking at applying materials in energy collection applications, energy storage applications. How you deploy the materials, how you design the system, where you create the services, their adjacency and connection with other parts of the system becomes a very, very important factor. And that aspect of design, that aspect of what's called in the electronics industry packaging, is a much less researched area, but is actually critical to the success of many materials, because you want to use the minimum amount of material to maximum effect. So for example, there are devices which absorb at one wavelength and re-emit at another wavelength, that are luminescent concentrators, and they are employed in photovoltaic applications and needed applications to get daylight into buildings and things like that. You can have those materials put within a monolithic material, so within an acrylic substrate, so you've got quantum dots in acrylic substrate, and that works effectively, okay? But the acrylic substrate itself has an extinction coefficient. Light gets reduced as it passes through it, okay? Another system is to actually have those quantum dots not in a matrix, not dispersed in a matrix of material, but placed on the walls of a light guide. And so that they absorb, they re-emit, but their transmission is then through air. And obviously the optical losses are zero because you're now transmitting through air rather than through a solid material. Now, because you've got the emitting materials at the walls of the system rather than within the system, the amount of material you can get is less. So you've got less conversion taking place, but you've also got far less losses. And there's a trade-off within that system. And that's just one example where how you choose to deploy new technology, whether you choose to deploy it within a medium that has other properties or in mediums that have very desirable properties, but the particular attribute of the technology is reduced because the amount you can put in the system, become very, very particular trade-offs. And that kind of work both in thermal energy storage, in a lot of quantum devices for spectral modification, in a whole range of applications around using near field effects to inhibit radiant heat transfer between systems, is an area which needs a lot more work and a lot more optimization. The opportunities for new materials are considerable, and they are, as I say, driven by aspects of trying to get better efficiency, lower weight, better storage capacity, lots and lots of factors. One key factor, however, that's coming through is less embodied energy. And this is important because in making things, there is energy from fossil fuels, etc., embodied in those materials, particularly if you look at things like cement, ceramics, glass, steel. A huge amount of energy goes into those materials, okay? And in certain contexts, the embodied energy is similar to the energy that the device uses operationally. So seeking to reduce the embodied energy is critically important. Now, we can do that at the process level, obviously alterations to the manufacturing process, or indeed electrify the process and supplying the electricity to the steel, cement, glass production from renewables. You do it at that end, okay? Nevertheless, at this point in time, there's still a lot of fossil energy embodied in current materials. And in the future, let's suppose that those manufacturing processes do electrify, there will be a lot of renewable energy consumed, indeed the majority of the renewable energy, consumed by those production processes. So seeking to reduce the use of those materials is going to reduce the amount of fossil fuels embodied, and in the future, reduce the need for excess renewable energy capacity that is not needed. So a lot of work is going on in seeking to have materials that are more bio-based, so cellulose, polysaccharides, those kind of materials, which are far more sustainable, are effectively carbon sinks if done correctly. And you're seeing that in certain energy storage systems like batteries, for example. You're seeing it in insulation systems, and you're even seeing it in some aspects of the substrates for photovoltaics. So a major strand is that aspect of looking at the overall environmental sustainability of materials. That also brings you to a whole lot of dimensions of how you track materials from their source, where they're extracted, where they're mined, where they're grown, all the way to their point of energy use. And so that you're including both the energy use of their extraction, their processing, and their transport. And that is a whole well-developing area. In a number of jurisdictions, I work in Ireland, which is in the European Union. The new regulations on building products, for example, the Energy Building Products Directive, requires European member states to introduce laws that will regulate the embodied energy in building materials. So these trends are happening, and they're in fact both in those countries, and indeed people who export materials to those countries in the future. So many diverse aspects of energy materials. What I want to draw as a conclusion is that materials science is one thing. I think material science always needs to be developed in the context of application, economics, and the wider environmental issues in terms of environmental safety, fire safety, toxicology, etc. And that needs to inform direction quite early on, okay? And there needs to be as much research in those areas as there needs to be in the fundamentals. And also, we need, from an educational perspective, to produce graduates who can have the design expertise to apply new materials in a way that minimizes the use of those materials and maximizes their effectiveness in end applications. Some of the insights I've provided today have come out of a whole range of projects, and for those of you who can do these things, if you look up my papers, you'll see the kind of publications and things that we do. We are supported by a whole range of organizations who I'd like to express my gratitude to. And I hope not having the slides has not been too bad. And I'm happy to answer any questions. Thank you very much indeed. Thank you.
Thank you so much, Professor Norton, for your insightful and inspiring talk. Are there any questions from the audience? Oh.
Thank you, sir. I just want to know, because India is a 1.4 billion country, so we have large human resource development activities here. So do you encourage joint projects with Indian researchers? And if, what is the modalities? And Indian government is also funding joint projects with different countries. We have MOUs with about 40 plus countries, maybe including Ireland also. So what about internship from Indian students at your place? Thank you, sir.
Could someone repeat the question, because there's a lot of echo in the room?
Yes.
Is it possible to repeat the question? Could maybe the...
Sir, we have large number of students studying in different courses in the country, and this area of energy material is a hot topic. So we would like to have a collaboration of Indian researchers with your team. This is one question. Second is whether you also encourage Indian students to be part of your organization as a training or as a project.
I still can't hear. The sort of the microphone at the who did the introduction. Her microphone works better. Maybe you just repeat the question from there, because there's just a big echo in the room. My apologies.
Yes. So is this audible? Hello?
Hello, yep.
Yes, sir.
Sir, we have a large number of students studying in different courses in the country and across different universities and institutions. And this energy materials is a hot area of research. So I just want to know whether there is a possibility of joint research activities between Indian researchers and researchers at your university. Number two, whether there are some opportunities available for Indian students to have some sort of internship or training, to have a collaboration or human resource development activity at least.
Okay, yeah, I understood. Apologies for getting you up on the stage. That's much clearer. Yes, I mean, generally, we work with PhD students and postdocs in my context, and we will have had students all over the world work with us as doing PhDs and doing postdoc positions. So that will be there. Having students as for shorter term visits is more difficult because we've got to slot them into existing projects. That can be a more challenging. But I'm always open to discussion and see what opportunities for collaboration there are. But certainly if there are students who would want to do PhDs, there are various funding schemes that support that. The challenge with shorter term visits and faculty exchanges, etc., is funding, okay? But certainly happy to discuss collaboration. And indeed, I collaborated with many colleagues in India over the years, been to India many times, and we've done research in India, particularly, for example, on PV cooling, on aspects of solar concentration, and some work on solar cooking, for example. So there's a lot of opportunity for collaboration. So if anyone's interested in collaboration, just write to me and we can discuss it. The main challenge is, because it does take time, the main challenge is developing new things that are going to get funded. Because the cost of it is the main issue. And certainly where I am, Ireland is a very expensive place to be, and it's important people are properly funded here so they can live properly. So that is the issue. But yeah, collaboration is something we do a lot of, and I would be keen to do more of. So happy to discuss. Easier at the PhD and postdoc level is my summary.